Okay, that doesn't sound like one up. And then I will, if there's time, I will show you how an integration approach can be applied. Okay, then, so we all know that if you have something that is V and then you've got R, the usual thing in IB is GMF R squared equals to MV squared. Yeah, so the idea is that you can run a low and the boring formula, just like this. Okay, so the thing is, most of the time in the world, it is not like this. Most of the time, it is the omelette. Alright, it's a elliptical omelette. Yeah, so it's a seafood. So one of the most important things that is one up from what you need to know right now is the conservation of angular momentum. Now, what on earth is this? Right? What on earth is this? If you had followed me through the Olympiad lessons, you will know that in rotational mechanics, or rather in linear mechanics, you've got F equals to FA. Yeah? And then there's this rotational equivalent which is torque. Torque sounds very scary, actually it is just moment. So moment is equal to the angular momentum, moment inertia times the angular acceleration, or the rate of change of angular momentum, where L is what we call angular momentum. Now what's the parallel for linear mechanics? It is the rate of change of linear momentum. So this is for linear, this is for angular. Now how is this relevant to this thing over here? Probably I'll just explain a little bit more about angular momentum. Now angular momentum, this is for solid body. Now moment inertia is something like a mass. It is the reluctance of a body to change its state of rotation. But what about, say for example, if you've got a point mass of mass m traveling at v from a point r over here. Now the angular momentum of this object is basically equals to mvr. Now how is it? Yeah.
Sir, but what's mean by angular momentum? Is it like the thing rotating, or is it go like the momentum around?
It is the ability of an object to okay, what is angular? I think it's probably easier for us to understand from what is momentum first, then we run up to what is angular momentum. Now momentum of body is related to the linear momentum is related to linear KE. Just like angular momentum is related to the rotational energy. So when something has rotational, that has angular momentum, it has the energy related to rotation. It can be anything. It can be the rotation of a rod about here. It can be the rotation of a sphere. You see, if I have something that's rotating over here, right, the center of mass doesn't move, so there's no half mv squared. But we know that there's energy. And if you perform integration of all the small little mass at different distances traveling at different speed, you'll find that it is actually the rotational energy. And the rotational energy is associated with rotational momentum, which is what we call angular momentum. There's no linear momentum for this object because the center of mass is not moving. Yeah. So there's no linear momentum, there's no linear KE, but there's rotational momentum, there's rotational KE energy. So it is the equivalent of rotational energy. Yeah. So something that has rotational momentum, angular momentum will have rotational energy. Does it mean that it can only have rotational energy and not kinetic energy? Not true. I can have a ball that's moving this way, rolling on the floor, and the CV moves. So if a ball were to move like this, then they will have both rotational energy, rotational momentum, and linear momentum and linear KE. So it's a combination of both. Okay? Now, the object, if it is a point mass over here, why would it have angular momentum? Why? I mean, this one I can understand because if you have something rotating, then there's something rotating. Right, for a point mass moving at a straight line, why would it have angular momentum? Now, this is easily understood if you have this object striking an object hinge here. Do you agree that when this object strikes this one, they will move together and rotate? So which means that before this thing even strikes this rod over here, it has the ability to cause rotation. Right? If it has the ability to cause rotation, it means that it must have a related quantity to rotation in terms of momentum. So that's why there is rotational momentum for this point mass above this point. Okay, so this is angular momentum. Now let's go back to the torque equals to this. If you look at the gravitational force, do you agree that gravitational force is always directed towards here? Regardless of where you are, it's always directed to here, which means that if I take moment about this point, what's the moment created by gravitational force? remember moment or not? We don't do moment in IB, but can't forget moment. Must remember moment.
Yes,
what's
sir.
the definition of moment? It's the product of
a force and perpendicular distance from the E to the P.
So what's the perpendicular distance of this force away from this point? It's a number. It's a number.
0.
0 is correct. So if the force passes through the pivot, it's always 0. Moment. So if the moment is 0, what's the rate of change of angular momentum?
0.
So the angular momentum of a body in orbital motion is always constant. Very important. L is constant. Have you heard of Kepler's second law? You have heard of Kepler's third law actually. Kepler's third law is?
Do you remember?
You derived it.
P squared proportional to R cubed.
T squared over R cubed. That's Kepler's third law. Kepler's second law, anyone?
The area that sits as constant.
Yes, the area that's swept is constant. So what happened is that per unit time, the area swept by this star is always a constant. Now actually that statement and this statement is the same. Try proving it. Right? Try proving it. That it is actually the same. The statement that Kepler's made that the area swept by the star or whichever that's in motion, orbital motion, the area swept by it per unit time is a constant, is the same as saying that the angular momentum of the object is constant. Okay, so how is this useful? Let me show you.
Angular
Acceleration.
And then I'll show you how is this being applied to this thing called a Hoffman transfer, which is still the method used. It's devised by someone in NASA, obviously someone called Hoffman. And then it's a method of transferring from one orbit to another orbit using elliptical orbit. Okay, then we'll go to that later. So if you got this, if I'm not wrong, this point is called the perigee, and this point is called the apogee. So let's just check on the internet right now and see whether I'm correct. Perigee and apogee. These 2 points. The nearest and the furthest. I think it's correct. Or is it going to be wrong? Someone is checking. Right? Okay, I'm good. Awesome. So what you can be asked, I'm not sure what in the question you can be asked, but I'm sure to show you relationship. Okay? So at this point, what you can write is that the GMM upon RA plus half MVA squared is equals to minus GMM upon RP plus half MVP squared. This is the usual one that you learn in IB, conservation language. Alright? And then the other one is, if this is RA and this is RP, then you can say that NVA RA is equals to NVP RP. Very clear? So the mass cancels off, this mass cancels off. And what you can do is, say for example, you want to find speed over here. VP is equals to, when you find VP, then you eliminate VA. RP, VP upon RA, and then you plumb this into here. So what you have then is you have minus GM upon RA plus GM upon RP equals to half VP squared minus half VP squared RP squared over RA squared. Therefore VP is equals to whatever it is. So I can actually find the speed of the object in this orbital speed, or this orbital orbit, in this elliptical orbit, if I know this distance and this distance. Once I know these two distances, I can actually compute the speed that I need at the perigee or the apogee. How is this useful? That's the key, right? I mean, you do all these things other than to impress people with how much you know about physics. What's the use? And this is the premise of Hoffman transfer. So say for example, you want to launch a satellite over here, and then you want to transfer it to a higher orbit. How? You're going to transfer it from orbit 1 to orbit 2. 怎么办? Stop it, push it vertically, and then push it again. Does it sound smart? No, seriously. It doesn't sound smart at all. It's like, push brake, stop it,
Oh.
kick it up, and then boom again. This doesn't sound clever at all, right? So how do you do it? Now, this is what Hofmann transfer is about. So at this point, you have a certain speed which is given by V equals to the square root of gm upon r, right? You have derived this 1,000 times already. Right. Okay, so this is for the circular orbit, which is the speed that it has over here. Remember, if you know the distance of the orbit over here, and you know the distance of the orbit over here, which you know, then this will become the perigee, this will become the apogee. So what all you need to do is to calculate the speed at this point, the perigee, change the speed of the satellite from this value to the new value over here, give it a punch, then you automatically go all the way here. But when it is at this point, you agree that in order for it to have a circular orbit, then it has a different v over here. But when you arrive here, it is the speed of the apogee. So you just need to give it another kick to change the velocity from the velocity at the apogee back to the velocity that is required to maintain circular orbit. So you just need to give it 2 kicks. Okay, there are 4 velocities that we're talking about here. Okay, V1, V2, circular, which is R1, R2, GMM upon R2. So to have circular orbit, it will have this speed at orbit 1, this speed at orbit 2, 1 and 2. You clear about that? Yeah. We know that if you maintain this speed, you always go in circular. You never go from 1 to 2, right? Or 2 to 1. So how do you kick it? So this one, if you solve it, you have this big expression in terms for the speed at the perigee in terms of R1 and R2. Right? So at this point, this is like the perigee of the orbital motion, of the elliptical motion, and this is the apogee. So you just need to kick it from V1c to this velocity. Do you agree that you will go from a circular orbit into an elliptical orbit that will fit nicely into here and here? Yeah? And then what happened then is, but when it reaches this speed, it is the speed of the apogee, which is what it has here. But that's not V2c. So you just need to give it another kick back into circular motion. Oh. Yeah. So this is Hofmann transfer. Okay. Very, very classic transfer technique. Use the most efficient. Yeah.
How is the okay? So you're boosting it to the apogee, right?
Yes, right.
But then why is that radius there as it goes to the like from the perigee to the apogee? Why is the radius there smaller?
That's why you like.
Oh, I see. But
It's likely to go like this and like this. It depends on the ellipticity. It may cut in over here. Yeah, it may cut in.
why? Wouldn't it just be going?
No, it shouldn't actually. It shouldn't.
Further out of the.
Yeah, it shouldn't because you're giving a bigger kick.
Yeah.
And it should go faster, so it go out and then cross in. Is it possible that it goes out and then somehow I think it goes up and then it catches at the top. At this point at the top. So it reaches it here. No. I think it reaches it on the opposite. I'm quite sure. You can search Hofmann transfer. I think it's the opposite end.
But so if you do the acceleration closer to the middle, right, then you can use that like I think they did in the Martian where like well, they go and then they did
That's slingshot.
The slingshot.
That's slingshot. Slingshot is a different thing. I'll come to that later. But this is basically a simple dynamics of the perigee apogee and how is it being used in practical application.
Then this acceleration would be in the direction of the circular motion.
Yes, correct. That means if the orbit, if the satellite is moving this way, then it should. I think it's a higher speed, so you kick it over here, and when it reaches here, you need to kick it here because the speed over here in the elliptical motion is lower than V2c. You need to accelerate it to V2c. V1c is lower than VP2, so you need to give it a kick to accelerate to VP. Then once it uses VP to reach VA, it is lower than V2c. So you need to give it another kick.
to the circle?
It
Like,
can.
how from that second kick, but how would you actually, like with a
All
satellite?
you need to make sure that is when it reaches this point, exactly this point, it is moving tangentially to the radial vector. It is already moving. Just that if you maintain the speed at VA, it will have a speed that is lower than that for a circular motion, so it will curve in. So it is not fast enough. That means the centripetal force will start pulling in from a circular orbit. That's why you need to give it that big kick. From a more layman's way of looking at it, it is a larger centrifugal force, so that it stops it from coming in.
But how, wouldn't that be like an instantaneous acceleration at that point?
You can say that yes,
But
it is
like,
actually using
that's-
rockets, a blast.
Is that possible?
It is possible. Very possible. It has been used many times already. Yeah. Read up more on it. It's, I think, spelled as HOFFMANN. I'm not sure whether there's double N or single N. Okay. So why not, think about this, why not send a satellite straight to the higher orbit? Why not straight away? Why transfer?
It's easier to accelerate in space.
Okay, that's one possible thing. And if you want to send something big into a higher orbit, sometimes they don't send it as one piece. They send it in multiple pieces. Then they meet and assemble it at lower orbit before they send it to higher orbit.
Wait, sorry.
Talking about slingshot, yeah.
That MVAR is the rotation.
Angular momentum.
Ah.
Angular momentum, angular momentum. Angular momentum over here and here are the same. In fact, everywhere they are the same. Just that we're interested in the nearest point and the furthest point.
Don't you have the pound for the spin of the earth as well?
Sorry?
Don't you have the pound for the spin of the earth as well?
Okay, the spin of the earth, yeah, okay.
Oh, that's simply constant.
The spin of the earth, why would it be important when you are off the earth?
Oh,
If you're going from the earth,
on spin of whatever object it is, it's spin momentum.
the spin of the earth shouldn't affect orbital motion. It shouldn't. But it does affect when you're sending a satellite from Earth to here. And that's why if you look at most of the launch of satellites, they try to launch it close to here. Because the ephemeral is actually lower, and also because there's a spinning effect with the Earth. That's why you look at America when they launch most of the things, they launch it near Mexico, at the southern end. But there's a certain limit when they release their rocket things so early. It goes too far south.
Doesn't the rotation of the object about its own axis also affect its angular momentum?
It does, but I guess comparing the speed that it is traveling over here and that means the I omega of the satellite on its own and MVR, this V is really big. So I guess it's insignificant. Yeah, because satellites spin. And why do satellites spin? Why do you think it's used? When they release the satellite, why do you think they always tend to spin? Accidental or intentional? When you spin, there is greater stability. Yeah, so that it doesn't wobble or it doesn't go out. Yeah. And that's why the gyroscopes, which they use for compasses, is a very big spin top. So this is very stable.
How do you keep adding? Because like when your thing is in orbit, your thing is
Fire.
not.
It's not literally a kick. It's
I know,
it's
but,
firing rockets.
but you have to keep rotating it as it goes, right? Because it will be facing one way the entire time. It wouldn't be spinning as well, right?
Okay, your question links right? I think that's
I don't know. Like,
so when the satellite is here, and then it goes, then it starts spinning like this. And then
no, I think like because you have like rather than spinning it like this way, you have to spin it this way as it goes around. Right?
oh, okay, so it's facing here, and then you got to face here.
Yeah, if you have to keep facing it.
It will not let. What happens is that if you have a satellite that's not spinning, it will be facing this way, facing this way, and facing this way. It will not always turn itself to face the satellite. It will not. So the way to go about this, if you want to maintain constant contact, you raise the antenna that's omnidirectional. It means if you want to maintain communication with the Earth, for whatever reason you want to always communicate with
Face the Earth.
yeah, you just face the Earth. Or you rotate the antenna to face the Earth, which is quite easily done. Regarding your gravitational slingshot, which is the one that is mentioned in mass, what happened is that basically you use the say the planet. So when you approach, when the planet is moving much faster, say V planet, and then your V satellite is probably very small. So what happened is that it uses the gravitational attraction to pull it inwards. So what happened is that basically the satellite is falling towards the planet and reaches the orbital speed of the planet. And what happened is that when it reaches the orbital speed of the planet, it slingshot itself away. That means it basically uses the loss in GPE of the planet to gain its own KE. But what happened is that the planet will lose KE. But don't fret, because the planet is usually much heavier than the satellite. So even if it loses KE, it will not crash into the sunlight. So that's what happens when you slingshot around a planet. Basically, you're zapping KE from the planet for your own use. You're basically falling towards the planet, and then you use that fall to gain KE, and then you accelerate out. A very common technique. In fact, the one that Cassini that goes out into deep space is slingshot about 2 or 3 planets as it goes for this round. Yeah. Basically stealing energy from the solar system. It's quite smart, right? Actually, if you think about it. How many of you have not watched the movie Mars?
The Martian.
Martian. How many of you have not watched Martian? Have all watched, Interstellar? How many of you have not watched Interstellar? Must go and watch. Okay? There are certain movies I would strongly encourage you to watch. Tenet. A little bit, yeah. Martian, Interstellar, should watch. Really. If you read up more on the Hopper transfer, there are different kinds of transfer. And the person who come up with the transfer, the way to transfer, the name is the method is named after the person. So there are many different methods of transfer. If you can come up with a very innovative way of transferring, it uses a very little amount of energy. Hung transfer. Hung transfer. Yeah. Hung transfer.
Short and sweet, sir.
Xia transfer.
Xia transfer.
Yeah. So it's named after the person. And that's what's mentioned in the Martian as well. The guy who came up with the way to slingshot. Yeah, actually it's real. Whenever a person comes up with an innovative way to transfer, it's named after the person. Okay, so hopefully one day I'll hear about your name. Big name. Yeah, a transfer big name after you. I think we have to call it an end. Next lesson on Monday, I'll show you how to compute the time it takes for satellite encountering atmospheric friction to crash into Earth. Using integration.
Sounds great, sir.
Sounds a bit ominous. Happy night. That's the gravity. Have you watched the movie where it's all about gravity? Yeah, gravity. Yeah, the last part where it just burns up in the atmosphere. Alright, people, nice thing to see again. Thank you, class.
Thank you.